Snap your fingers. In that brief instant, a beam of light would have circled the Earth 7 times. 7 complete laps around a planet in less time than it takes to blink. 299, 792, 458 meters per second. The fastest thing in the universe. The ultimate speed limit. The gold
Expanding the
standard we
silicate
revere
layer
and
now.
aspire to. But here's the truth.
The
few are willing to
3D/Atlas
admit.
structure
On the
is
grand
highly
scale of the
unstable at
cosmos,
this depth.
The speed of light is not fast. It's painfully, tragically, and frighteningly slow, a snail creeping across a continent. And the light year, that unit we casually toss around, is not a measure of exploration. It is the thickness of the prison walls that confine us. The sun you see now is 8 minutes old. If it vanished right now, you wouldn't know for 8 minutes. You would finish your coffee, kiss your child, fret over your taxes. Mars, orbiting a star that no longer exists, is 20 minutes away at light speed. An astronaut crying out for help would wait 40 minutes for a response. By that time, they would already be dead. The nearest star is 4 years away. Or trio half-years. 000 years at the speed of our fastest rocket. The farthest reaches of our galaxy are 100,000 light-years away. The light we see tonight from there shows Earth before humans ever walked the planet. We are prisoners. The cage is made of the very laws of physics. And the bars are growing tighter as the universe expands faster than we can ever hope to follow. Can we escape? Or are we destined to perish on this rock, gazing at stars we can never reach? Chapter 1. The Illusion of Instant. But before we begin, don't forget to subscribe. If you truly enjoy these videos, please leave a like. Let's begin. Snap your fingers. In that brief instant, the sound traveling from your hand to your ear, a beam of light could have completed 7 full circuits of the Earth, 7 laps around a planet, nearly 40, 0 kilometers in circumference, to a creature of flesh and blood, whose fastest runners cover 100 meters in under 10 seconds. The speed of light seems like magic. It is instantaneous. It is the speed of thought. It is the cosmic speed limit written into the fabric of reality itself. 299, 792, 458 meters per second. That is the precise number. Not roughly, not approximately, but exactly. In 1983, scientists decided to define the meter itself based on the speed of light. The distance light travels in 1/299. 792, 458 of a second became the new meter. The speed of light is no longer something we measure, it is the standard by which we measure everything else. For centuries, humanity has worshipped this speed. We view it as the gold standard of the cosmos. We design our fiber optic cables to carry information close to this speed. Our computer chips are built with the knowledge that electrical signals crawl through circuits at fractions of this pace. We dream of interstellar travel and imagine ships that might one day approach this ultimate barrier. We look at the stars scattered across the night sky and think, if only we could go that fast, the universe would be ours. It's a beautiful thought, but it's also a lie. We're about to take a journey that will shatter your understanding of speed. We're going to show, step by step, measurement by measurement, that on the scale of the cosmos, the speed of light is not fast. It's not swift. It's not the racing stallion we imagine. It is agonizingly, tragically, and terrifyingly slow. It's a snail creeping across a continent. It's a glacier inching down a mountain valley. It's molasses in January, and the light year, the unit of measurement we casually toss around, is not a measure of exploration. It's the thickness of the prison walls that surround us. Every light year between us and another star is a year of travel at the fastest speed physics allows. Every light year is a gap that mocks our ambition. Consider the sun, that blazing ball of nuclear fusion that dominates our sky, warms our skin, and makes life possible on this planet. It feels immediate. It feels present. You walk outside on a summer day, and the warmth hits your face, and you think, there is the sun, right there, shining down on me. But it is not right there. The light hitting your eyes at this very moment left the surface of the sun 8 minutes and 20 seconds ago. You are not seeing the sun as it is. You're seeing a ghost. You're seeing where the sun was. If the sun were to suddenly disappear, if some cosmic force deleted it from existence right now, you wouldn't know. For 8 minutes and 20 seconds, the sky would remain blue. Flowers in your garden would continue photosynthesizing. The gravity holding Earth in its orbit would still function because gravitational waves also travel at the speed of light. You'd finish your coffee. You'd check your phone. You'd worry about your meeting this afternoon. Then, without warning, darkness would descend. The sky would turn black. The temperature would plummet, and Earth, freed from its gravitational tether, would be flung into the void like a stone shot from a sling. This 8-minute gap is the first crack in our perception of reality. It's the first clue that we're disconnected from the present moment of the universe. We don't live in the present moment. We live in its recent past. Every observation we make, every photon that enters our eyes, carries information that's already history by the time it reaches us. But 8 minutes is manageable. 8 minutes is a coffee break. 8 minutes is the time it takes to heat up a frozen meal. We can wrap our heads around 8 minutes. Now, let's step further out. Let's leave the comforting warmth of our local star and head toward the next object in our cosmic ambitions. Let's go to Mars. Mars is our dream. It's the planet we've covered with robotic explorers. It's the world we hope to use as our first outpost beyond Earth. We talk about becoming a multi-planetary species. We imagine domed cities, terraformed landscapes, and internet connections bridging the gap between worlds. Elon Musk builds rockets. NASA drafts plans. The collective imagination of humanity stretches toward that red dot in the night sky. But we forget the lag. At its closest approach, when Earth and Mars are on the same side of the Sun, Mars is about 3 light minutes away. At its farthest, when the two planets are on opposite sides of the Sun, the distance stretches to over 22 light minutes. Imagine you're an astronaut on Mars. You're the culmination of a century of space exploration. You stand on the red soil, gazing at a pink sky. And then something goes wrong. A seal breaks. An alarm blaze. The atmosphere is leaking from your habitat. You're going to die unless you fix it in the next few minutes. You shout into your radio, "Houston, we have a problem." Your voice, encoded into radio waves, travels at the speed of light. The fastest thing in the universe, it races across the vacuum of space, taking 20 minutes to reach Earth. In Houston, the flight controller is drinking his coffee. He hears your distress call 20 minutes after you made it. 20 minutes after you began suffocating, he presses the transmit button. "We read you. Mars, here's how to fix the seal. Follow these steps." His instructions race back at 300. "Niche kilama, sir." Another 20 minutes pass. "Arvest in total." You're already dead. The speed of light killed you. This is the reality of space travel that science fiction ignores. There's no conversation in space at these distances. There's only history. Every message sent is a bottle thrown into a black ocean, hoping someone finds it and hoping it's not too late when they do. To conquer the solar system, we must accept that we will never truly speak to one another in real time again. We'll only leave voicemails. Now consider Voyager 1, launched in 1977. It's the fastest object humanity has ever created. It's been flying for almost 50 years. It travels at 61. Nulla came us. It's left all the planets behind. It's crossed the boundary where the solar wind gives way to interstellar space. It's in the great dark beyond. And in terms of light speed, it's pathetic. Voyager 1 is currently about 22 light hours away from Earth. Not light years, light hours. It hasn't even reached a full light day's distance, the edge of our solar system. The vast spherical cloud of icy debris called the Oort cloud extends out to roughly 1 light year. Light itself, the fastest thing in existence, takes an entire year just to travel from the sun to the outer edge of our cosmic neighborhood. Think about that scale. If you turned on a flashlight today and aimed it at the edge of the Oort cloud, you'd have to wait 12 months for that beam to reach it. A full trip around the sun. Seasons changing. Holidays passing. A year of your life. While a beam of light crawls toward the edge of our backyard. Beyond that edge lies the abyss, the true void. The nearest star system, Alpha Centauri, floats in that darkness. Sir, 24 light years away. Not light hours, not light days, light years. 4 years and 3 months of travel at the ultimate speed limit of physics. Just to reach the nearest neighbor in a sea of stars. If the sun were the size of a grain of sand, Earth would be a microscopic speck of dust 3 centimeters away. On this scale, with this tiny sun and this invisible Earth, Alpha Centauri would be another grain of sand, 30 kilometers away. And between those 2 grains of sand, between our sun and the nearest star, there is absolutely nothing, just 30 kilometers of empty, howling void. We are not explorers sailing between islands in a tropical sea. We are castaways on a speck of rock, surrounded by an ocean so vast it might as well be infinite. The fastest ship we could ever build, traveling at the maximum speed the universe allows, would take over 4 years just to reach the nearest shore. The speed of light is not nearly fast enough. It is far too slow. It crawls across distances that make a mockery of biological life and its fleeting existence. And we haven't even begun to grasp the true scale of our confinement. We haven't even left the neighborhood. The galaxy awaits. The universe awaits. And they are vast beyond human comprehension. But to understand how we came to these harsh truths, we must go back to the beginning. We must rewind to a time when humanity didn't know light had a speed at all. We must travel back to 1676, to a Danish astronomer gazing at Jupiter's moons, on the verge of a discovery that would change everything we thought we knew about the cosmos. Chapter 2. The First Measurement. For much of human history, we believed light traveled instantaneously. The ancient Greeks debated the question but never reached a consensus. Aristotle thought light wasn't movement at all, but the presence of something, a state of being, not a traveling entity. Centuries earlier, Pythagoras had suggested light might have a finite speed, but he had no evidence to prove it. The debate remained a matter of philosophy, untethered from experimentation. In the early 1600s, Galileo Galilei tried to settle the question. He devised an experiment that was elegantly simple. 2 people would stand on hilltops, a known distance apart. Each would hold a covered lantern. The first person would uncover their lantern, and when the second person saw the light, they would uncover their own. Galileo would then measure the time it took for the second lantern to light up in response. From this delay, he hoped to calculate the speed of light. The experiment failed utterly, not because the method was fundamentally flawed, but because the distance was too small. Even if Galileo had placed his observers 10 kilometers apart, the light would have made the round trip in just about 66 microseconds. Far too fast for human reflexes to detect. Galileo could only conclude that if light had a speed, it was extraordinarily fast, at least 10 times faster than sound. He was wrong, but only by a factor of about 1 million. The breakthrough came from an unexpected source, not someone trying to measure light directly, but someone solving a practical navigation problem. Ole Rømer, born in Etersinde av 644 in Aarhus, Denmark, grew up during a period when astronomy was transforming from mystical stargazing into a rigorous mathematical science. Tycho Brahe had spent decades making the most precise astronomical observations in history, and Johannes Kepler had used that data to derive the laws of planetary motion. Galileo had pointed his telescope at Jupiter, and discovered 4 moons orbiting the giant planet. These moons, now called the Galilean moons, became objects of intense study. Io, the innermost and fastest of Jupiter's moons, completed an orbit around the planet every 42.5 hours. Like clockwork, regular and predictable, Galileo himself suggested that these moons could serve as a cosmic clock. If you could precisely predict when Io would pass behind Jupiter and then time that eclipse from wherever you were on Earth, you could determine your longitude. This was hugely important for navigation, as sailors were being lost because they couldn't accurately determine their position at sea. Romer travelled to the Paris Observatory in 1671 to work on this problem. He spent years compiling meticulous observations of Io's eclipses. He wasn't trying to measure the speed of light, he was just trying to better predict when the eclipses would occur. But in his data, he noticed something strange. The timing of Io's eclipses was inconsistent. When Earth was on the same side of the Sun as Jupiter, moving toward the giant planet, the eclipses occurred earlier than predicted. When Earth was on the far side of the Sun, moving away from Jupiter, the eclipses happened later. The difference was small but measurable, over 6 months, as Earth swung from one side of its orbit to the other. The accumulated discrepancy reached about 22 minutes. Romer couldn't explain this by any irregularity in Io's orbit. The moon's orbit was steady. The variation had to come from somewhere else. And then he realized the truth. The variation came from Earth's changing distance from Jupiter. When Earth was closer to Jupiter, light from the eclipse had less distance to travel and arrived sooner. When Earth was farther from Jupiter, the light had to cross the additional width of Earth's orbit, arriving later. The timing difference wasn't a measurement error, it was a measurement of how long it took light to travel across the diameter of Earth's orbit. On November 21st, Romer presented his findings to the French Academy of Sciences. He had predicted that an eclipse of Io, scheduled for November 9, would be 10 minutes late. He was right. The eclipse occurred exactly when his calculations said it would, proving that light took time to travel. Romer estimated that light required 22 minutes to cross the diameter of Earth's orbit. The Dutch scientist Christian Huygens took this estimate and combined it with the best available measurement of Earth's orbital diameter. He calculated that light travelled at approximately 220 km/s. This was the first measurement of the speed of light in human history, and it was wrong not conceptually, but numerically. The actual speed is closer to 300 km/s, about 35% faster than Huygens calculated. The error stemmed from 2 sources. First, Romer's estimate of 22 minutes was too high. The actual time is closer to 16 minutes. Second, the diameter of Earth's orbit was not precisely known in 1676. However, the fundamental insight was correct. Light had a finite speed. It was fast beyond ordinary comprehension. But it wasn't infinite. It wasn't instantaneous. It took time to travel, and that time could be measured. This discovery would have profound implications. But humanity wouldn't fully understand them for another 2 centuries. If light has a speed, then we never see the universe as it is. We see it as it was. The farther away an object is, the older the image we receive. When we look at the sun, we see it 8 minutes in the past. When we look at a distant star, we see it years, decades, or centuries ago. When we look at a galaxy, we see it millions of years in the past. The universe is not a snapshot. It's a layered archive of history. Every direction we look backward in time. But Romer's discovery also raised a troubling question that wouldn't be answered until 1905. If light has a speed, what is it moving through? Sound moves through air. Ocean waves move through water. What medium carries light across the vacuum of space? Physicists invented a substance called the luminiferous ether, imagining it as an invisible, intangible material that filled all of space. Light, they theorized, was a wave in this ether. Just as sound is a wave in air, the ether had to be everywhere, permeating all matter because light could travel through the emptiness between planets and stars. This theory seemed reasonable, it fit with everything scientists knew about waves, but it made a specific prediction: if Earth was moving through the ether as it orbited the Sun, the speed of light should differ depending on the direction you measured it. Moving with the ether current, light should be slightly faster. Moving against it, slightly slower. Just like a boat moves faster downstream than upstream. In 1887, Albert Michelson and Edward Morley set out to detect this difference. They built an incredibly sensitive instrument that could measure variations in the speed of light as small as a few kilometers per second. They measured the speed of light in different directions at various times of the year as Earth moved in different directions through space. They found nothing. The speed of light was exactly the same in every direction. Always, without exception. It didn't matter which way Earth was moving or what time of year it was. Light always traveled at the same speed. This result baffled physicists. It seemed to defy the basic principles of how motion worked. If you were on a train moving at 100 kilometers per hour and you threw a ball forward at 20 kilometers per hour, an observer on the ground would see the ball moving at 120 kilometers per hour. The velocities would add. That's common sense. That's how the world works. But light did not behave this way. If you were on that same train and turned on a flashlight, the light would not move at 300. 0 km par seconde, plus 100 km par heure. It would move at exactly 300. Nietzsche kiloma. Sir. Period. The velocity of the source made no difference. Many physicists tried to explain this paradox. Hendrik Lorentz and Henri Poincaré developed mathematical transformations that could account for the null result of the Michelson-Morley experiment while still preserving the ether theory. Their equations worked, but they were awkward patches on a theory that was starting to show cracks. The true answer came from a 6-year-old patent clerk in Switzerland. A young man who spent his days reviewing technical applications and his evenings thinking about light. His name was Albert Einstein, and he was about to overturn 2 centuries of physics with 2 simple postulates. The year was 1905. It would later be called Einstein's miracle year. And the paper he published that September would change not only our understanding of light, but our understanding of space-time and the very nature of reality itself. Chapter 3. Einstein and the Absolute Limit. Albert Einstein was not a typical scientist of his era. He had struggled to find academic employment after graduating from the Swiss Federal Polytechnic. He worked as a tutor, a temporary teacher, and finally as a technical examiner at the Swiss Patent Office in Bern. It was a modest position, respectable, but hardly prestigious. His colleagues in the physics world, those with university appointments and laboratory access, might have looked down on the young patent clerk toiling away on the 3rd floor of the Postal and Telegraph building. But Einstein had something more valuable than a laboratory. He had thought experiments. He could construct entire universes in his mind, populate them with physical laws, and watch what happened when those laws collided with logic. He had been running these mental experiments since he was 16 years old, when he first wondered what would happen if you could chase a beam of light. Imagine, he thought, that you could run alongside a light wave, matching its speed exactly. What would you see? According to classical physics, you should see a frozen electromagnetic wave. The electric and magnetic fields should be suspended in space, oscillating neither forward nor backward, a snapshot of light, motionless beside you. But this was impossible. James Clerk Maxwell had shown that light was an electromagnetic wave, and his equations did not allow for frozen waves. A stationary electromagnetic field would not be light at all. It would be something else entirely, something that did not exist in Maxwell's framework. This contradiction haunted Einstein for years. Either Maxwell's equations were wrong, or something fundamental about the relationship between motion and light was wrong. Einstein bet on the second option. In September of 1905, Einstein published a paper titled on the electrodynamics of moving bodies in the German physics journal Annalen der Physik. The paper was unusual from the start. It contained no experimental data. It cited almost no references. It was built entirely on logic, starting from two postulates that Einstein declared to be true and relentlessly following them to their conclusions. The first postulate was the principle of relativity. The laws of physics are the same for all observers in uniform motion relative to one another. If you are in a smoothly moving train car with no windows, there is no experiment you can perform that will tell you whether you are moving or stationary. All inertial reference frames are equivalent. The second postulate was the principle of the constancy of light. Speed light in a vacuum always travels at the same speed, regardless of the motion of the source or the observer. Whether you are standing still, running toward a light source, or flying away from it at half the speed of light, you will always measure that light moving past you at exactly 299. 797 kilometer. These two postulates seemed simple, almost innocent, but taken together, they demolished the Newtonian worldview that had reigned for over 200 years. Consider what happens when you try to reconcile these postulates. Imagine a train moving past a station platform. A passenger on the train turns on a flashlight and shines it forward. According to the second postulate, an observer on the platform should measure that light moving at the speed of light. Not the speed of light plus the speed of the train, just the speed of light. And the passenger on the train, measuring the same beam, should also get the speed of light. Not the speed of light minus the speed of the train, just the speed of light. How can both observers be right? The answer is that they are measuring with different rulers and different clocks. Space and time themselves behave differently for observers in relative motion. Einstein showed that to keep the speed of light constant for all observers, time must slow down for moving objects. This effect is called time dilation. The faster you move relative to another observer, the slower your clock ticks compared to theirs. This is not an illusion. This is not a measurement error. This is physical reality. Moving clocks tick slower. Einstein also showed that moving objects contract in the direction of their motion. This is called length contraction. A meter stick flying past you at high speed is physically shorter than a meter stick at rest. Again, this is not an illusion. Physical reality. Moving objects are shorter. These effects are tiny at everyday speeds. At 100 kilometers h, time dilation and length contraction are so small they are undetectable. But as you approach the speed of light, they become dramatic. At 90% of light speed, time slows to less than half its normal rate. At 0,1%, it slows to about 17%. At 0,1%, it slows to about 12%. And this is where the prison bars begin to appear. As an object accelerates toward the speed of light, its mass increases, not its rest mass, but its relativistic mass, the effective mass that determines how much energy is needed to accelerate it further. The faster you go, the harder it becomes to go faster. At 90% of light speed, your effective mass has more than doubled. At 0,1%, it has increased sevenfold. At 0,1%, more than 20 times. To reach the speed of light itself, your mass would become infinite. You would need infinite energy to accelerate an infinite mass. This is physically impossible. Therefore, nothing with mass can ever reach the speed of light. This is not an engineering limitation. This is not a matter of building better rockets or discovering more efficient fuel. This is the fundamental nature of space and time. The speed of light is not just the speed at which light happens to travel. It is the speed limit of causality itself. It is the speed at which any massless particle, any form of electromagnetic radiation, or any gravitational wave must travel. It is woven into the fabric of space-time. Einstein derived from his postulates the most famous equation in physics: energy equals mass times the speed of light squared. M2 equal mc². This equation reveals that mass and energy are interchangeable, that matter is frozen energy, and energy is liberated matter. The conversion factor is the speed of light squared. Because CCC is so enormous, even a tiny amount of mass contains a staggering amount of energy. This is why nuclear weapons are so destructive. This is why the sun can burn for billions of years. This is the equation that defines the energetics of the universe. However, the equation also reveals why faster than light travel is forbidden. To accelerate a massive object to the speed of light would require converting an infinite amount of energy into kinetic energy. The universe does not contain an infinite amount of energy, so the acceleration can never be completed. In 1915, Einstein extended his special relativity into a general theory that included gravity. He showed that mass and energy curve space-time, and that what we perceive as gravitational attraction is actually the curvature of space and time around massive objects. Light follows this curvature. Time slows down in gravitational fields. And nothing, not even gravity itself, can transmit information faster than light. This last point is crucial. Gravity travels at the speed of light. If the sun were to suddenly vanish, Earth would continue in its orbit for 8 minutes and 20 seconds. Not because gravity is slower than light, but because gravity is exactly as fast as light. Both carry information about the state of the universe, and both are limited to the same maximum speed. We are prisoners not just of distance, but of causality. We cannot know about events faster than light can bring us news of them. We cannot act on distant locations faster than light can carry our influence. We are isolated bubbles of awareness, floating in a cosmos where the speed of light defines the boundaries of the knowable. By 1915, the theoretical framework was complete. The speed of light was the ultimate limit. Nothing could exceed it. Nothing could even reach it. And that speed, while unimaginably fast by human standards, was agonizingly slow when measured against the distances of the cosmos. Now, let us turn our attention outward. Let us survey our solar system and see how the prison of light speed manifests even in our own backyard. Let us count the minutes and hours that separate us from our nearest neighbors and understand why the dream of a spacefaring civilization must contend with the tyranny of distance. Chapter 4. The Solar System Delay. Let us begin a journey outward from the sun. Let us measure our solar system, not in kilometers or miles, but in the currency that truly matters: light time. The time it takes for a photon, traveling at the maximum permitted speed of the universe, to cross from one point to another. The sun sits at the center, massive, blazing, generating energy through nuclear fusion at a rate of 8 times 10263. 8 times 2, 26 8,026 watts. More energy is released in a single second than human civilization has consumed in all of recorded history, and yet that titanic output takes time to reach us. From the surface of the sun to the surface of the Earth, light travels for 8 minutes and 20 seconds. This is our starting point, our baseline. The star that makes our existence possible floats 8 minutes in the past whenever we look at it. You have never, in your life, seen the sun as it actually is at this moment. You have only ever seen its recent history. Moving outward, we encounter Mercury, the innermost planet, scorched on one side, frozen on the other, orbiting so close to the sun that its year lasts only 88 Earth days. At its closest approach to Earth, Mercury is about 3 light minutes away. At its farthest, when the sun stands between us, it's about 13 light minutes. A message to a hypothetical probe on Mercury would take between 3 and 13 minutes, depending on orbital positions. A reply would take the same. The fastest possible conversation would take between 6 to 26 minutes per exchange. Venus comes next, often called Earth's twin for its similar size and mass. Though its surface is a hellscape of sulfuric acid, clouds, and temperatures hot enough to melt lead, Venus swings between about 2 and 15 light minutes from Earth. During its closest approaches, a signal to Venus and back takes roughly 4 minutes. At conjunction, when the Sun blocks the path, communication is impossible until the geometry improves. Then, Mars, our dream, our obsession, the planet where we have already placed rovers and landers, where we plan to send humans within the next few decades. At its closest, Mars is about 3 light minutes from Earth. At its farthest, over 22 light minutes. The average is around 12 light minutes. Consider what this means for a crewed mission. When astronauts land on Mars, they will be functionally alone. Their communication with Earth will resemble a very slow email exchange, not a phone call. A message sent from Mars takes between 3 and 22 minutes to arrive, depending on the planet's positions. A reply takes the same. If an astronaut asks a question during breakfast, the answer might arrive during lunch or dinner, or the next day. If the orbital geometry is particularly unfavorable, every decision that requires input from Earth will be delayed by a minimum of 6 minutes and a maximum of 44 minutes. In an emergency, this delay could be fatal. A fire, a medical crisis, a structural failure, any situation where minutes matter, the astronauts will have to handle it alone. They will have to be trained to be autonomous. They will carry the knowledge and skills that would normally reside in mission control. Mars colonists will not be explorers in contact with home. They will be settlers, effectively cut off from the world that sent them. Beyond Mars lies the asteroid belt, that sparse ring of rocky debris between the orbits of Mars and Jupiter. The largest object in the belt, the dwarf planet Ceres, averages about 17 light minutes from Earth. Asteroids closer to the inner edge of the belt might be 10 light minutes away during favorable alignments. Those near the outer edge, approaching Jupiter's orbit, could be 30 minutes distant. Jupiter dominates the outer solar system, 11 times the diameter of Earth, more massive than all other planets combined. Its gravity has shaped the architecture of the solar system, flinging comets inward and asteroids outward, creating and destroying. At its closest approach, Jupiter is about 33 light minutes from Earth. At its farthest, roughly 53 light minutes, the Galileo spacecraft, which orbited Jupiter for 8 years in the 1990 seconds and 2000s, operated with round-trip communication delays of over an hour at times. Commands sent from Earth took half an hour to arrive. Confirmation that those commands had been executed took another half hour to return. Saturn, with its magnificent rings, floats even farther out. At minimum distance, Saturn is about 66 light minutes from Earth. At maximum, 91 light minutes, 1.5 hours. The Cassini mission, which spent 13 years exploring the Saturnian system, could not be micromanaged from Earth. Controllers had to send sequences of pre-programmed instructions and trust the spacecraft to execute them. Real-time control was impossible. The delay was simply too long. Uranus and Neptune occupy the frigid outer reaches of the solar system. Uranus, at its closest, is about 2.5 light hours from Earth. Neptune, about 4 light hours away. The Voyager 2 spacecraft, the only human artifact to visit both ice giants, sent back images that took hours to reach us. When Voyager 2 made its closest approach to Neptune in 1989, the signal carrying those historic images traveled for over 4 hours through the void before reaching the radio dishes of the Deep Space Network. And then there's Pluto, demoted from planetary status, but no less distant for its reclassification. The New Horizons spacecraft flew past Pluto in 2015 after a journey of 9.5 years. At the moment of closest approach, Pluto was roughly 4.5 light hours from Earth. The signal confirming that New Horizons had survived the encounter took 4.5 hours to arrive. Scientists on Earth waited, helpless, not knowing whether their spacecraft was alive or dead, while photons crawled across the abyss at 300. Niche Kilama. Sir, beyond Pluto stretches the Kuiper Belt, home to icy worlds and dormant comets, and beyond that, the hypothetical realm of the Oort cloud, a spherical shell of debris that might contain trillions of icy objects. The inner edge of the Oort cloud is thought to begin at roughly 2,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun. About 8 light minutes are 000 astronomical units is roughly 11 light days. The outer edge of the Oort cloud might extend to 50,000 astronomical units or more. Nearly a light year from the Sun. A light year of debris and darkness and cold. Voyager 1, our fastest emissary, traveling at over 61. Nuala came. Will not reach the inner cloud for another 300 years. It will not exit the outer edge for another 30,000 years, at which point it will still be nowhere near another star. This is our solar system. This is our backyard. And it takes light minutes to hours to cross even its inner reaches, light days to cross its outer suburbs, nearly a light year to traverse its full extent. Every robotic mission we send to the outer planets operates in what engineers call store and forward mode. We send instructions, then wait. The spacecraft executes those instructions, then sends back results. We analyze those results, then send new instructions, and wait again. The process is slow and painstaking. It requires extraordinary patience and planning. It requires spacecraft smart enough to handle contingencies on their own, because help from Earth is always minutes or hours away. For human exploration, the implications are stark. Traveling to the outer solar system would mean traveling beyond the reach of real-time support. A crewed mission to Jupiter would be a mission into isolation. The astronauts would have to be self-sufficient in ways no human crew has ever been. They would have to be their own mission control, their own doctors, their own engineers. They would have to solve every problem that arose with whatever they had on board, because by the time Earth even learned of the problem, they would have had to solve it or die. And Jupiter is still inside the solar system. Jupiter is still our immediate neighborhood. The stars are incomprehensibly farther. The nearest star, Proxima Centauri, 24 light-years away, would require over 4 years of travel, even at light speed. At the speed of our fastest spacecraft, over 70,000 years. But before we venture to the stars, let us understand what lies between them. Let us comprehend the true nature of interstellar space. Let us stare into the void and see just how vast, empty, and hostile it truly is. Chapter 5. The Interstellar Void. Imagine you could shrink the sun down to the size of a grain of sand, a tiny yellow speck, no larger than a pinhead, sitting on a table in front of you. At this scale, Earth would be a microscopic mote of dust, barely visible even under magnification, orbiting about 3 centimeters away. Jupiter, the largest planet, would be a small grain of powder, perhaps 30 centimeters distant. Neptune would be almost a meter away, a nearly invisible fleck in the darkness. Now comes the question that reveals the true horror of interstellar distances. At this scale, where the sun is a grain of sand and our solar system fits on a modest tabletop, where is the nearest star, Proxima Centauri? The closest stellar neighbor to our sun would be another grain of sand sitting approximately 30 kilometers away. 30 kilometers of empty space between 2 grains of sand. If you placed your model sun in the center of London, the nearest star would be somewhere near Oxford. If you placed it in Manhattan, the nearest star would be past Philadelphia. And between those 2 grains of sand, there is nothing. No planets, no asteroids, no comets. Nothing but a howling vacuum of nearly absolute zero temperature and nearly perfect emptiness. The density of matter in interstellar space is so low that you could pass through a cube of it, 100 kilometers on each side, and encounter only a handful of atoms, mostly hydrogen, plus traces of helium and cosmic dust. A few scattered particles in a volume of space larger than most countries. This is the void. This is what separates us from every other star in the galaxy. Not a sea to be crossed. Not a desert to be traversed. An abyss so empty it defies comprehension. Proxima Centauri is Patru, 24 light-years away. That means light traveling at 300. 0 kilometers per second takes 4 years and about 3 months to make the journey. A beam of light leaving Proxima Centauri today will not reach Earth until sometime in 2030. Depending on when you read this, any signal we send, any message we transmit, will take over 4 years to arrive and 4 more years for a reply. The fastest possible round-trip communication time with our nearest stellar neighbor is 8.5 years. Consider what that means. If intelligent beings lived on a planet orbiting Proxima Centauri and they were listening for our signals, the message would have to be worth waiting nearly a decade for a response. Hello, we exist. 8.5 years later. Hello, we exist. 2. How are you 8.5 years later? We are well. How are you? A simple exchange of pleasantries would take a quarter century. A meaningful conversation would span generations. And Proxima Centauri is the closest star. The Alpha Centauri system, of which Proxima is a part, contains 2 other stars. Alpha Centauri A and B, slightly farther at 37 light-years. Beyond that, the distances only grow. Barnard's star is 6 light-years away. Wolf 359 is 7, 9 light-years away. Luiten 2, 1185 is 8, 3 light-years away. Sirius, the brightest star in our night sky, is Kardec Sun, 6 light-years away. When you look at Sirius tonight, you are seeing light that left that star when your children were toddlers, or before they were born. You are seeing the past made present by the slowness of light across the void. Within 10 light-years of our Sun, there are roughly a dozen star systems. Within 20 light-years, perhaps 100. Within 100 light-years, tens of thousands. Each one separated from us by years of travel at the maximum speed the universe allows. Each one isolated by the prison of light speed. How long would it take to actually travel to these stars? Let us begin with Voyager 1. The fastest object humanity has ever launched on an escape trajectory from the solar system. Voyager 1 travels at about 17 kilometers per second relative to the Sun, roughly 61. Nulla Kima Arsh. At this speed, it would take Voyager 1 approximately 73,000 years to reach Proxima Centauri. Tisha-san, 000 years. Anatomically, modern humans first appeared in Africa roughly 300,000 years ago. The oldest known cave paintings are about 64,000 years old. Agriculture was invented about 12,000 years ago. Written language about 5,000 years ago. If we had launched a spacecraft toward the nearest star when the first humans were painting bison on cave walls in France, that spacecraft would still be traveling today. It would not have arrived yet. It would not arrive for another 9,000 years. At Voyager speed, a trip to Sirius would take over 140,000 years. A trip to a star 100 light-years away would take nearly 2 million years. The human species would likely have evolved into something unrecognizable or gone extinct entirely before the mission was complete. Even if we could build much faster spacecraft, the timescales remain daunting. Imagine a ship that could travel at 1% of the speed of light. This is vastly beyond our current capabilities. It would require energy sources we have not yet invented and propulsion systems we can barely conceive. But grant us this miracle technology at 1% of light speed. Sanche, Nich kilome, se. A trip to Proxima Centauri would take 424 years, still longer than any human empire has ever lasted, still longer than the entire history of the United States several times over. What about 10% of light speed? Now we are in the realm of science fiction. A ship moving at 30 million meters, s. The kinetic energy of such a ship, even a modest one of 1,000 tons, would be equivalent to multiple nuclear weapons. The engineering challenges are staggering, shielding against interstellar dust, which would strike the hull like machine gun fire at such speeds, deceleration at the destination, which requires as much energy as acceleration at departure, navigation through a void where the nearest landmark is still years away, even at 10% of light speed. The journey to Proxima Centauri would take 42 years. A human could conceivably make that trip if they departed young and arrived old. Their children could greet a new star if they were born along the way. But the travelers would leave behind everyone and everything they knew. They would arrive at a world where their friends and family had aged by the same 4 decades, but where no communication had been possible for the entirety of the journey, where every message sent home took over 4 years to arrive and over 4 years to be answered. At 50% of light speed, still well beyond any technology we can imagine, Proxima Centauri is 8.5 years away. At 90% of light speed, about 4.7 years. Only at 99% of light speed does the journey time drop below 4.5 years from the traveler's perspective. Though time dilation makes this number somewhat misleading, and all of these scenarios assume propulsion systems that do not exist, energy sources that we cannot produce, and solutions to engineering problems we have not even begun to solve. The fastest spacecraft currently under serious development, the Parker Solar Probe, reaches speeds of about 175 kilometers per second relative to the Sun during its closest approaches. This is extraordinarily fast by human standards. It is still only about 0.6% of the speed of light. At Parker Solar Probe velocities, Proxima Centauri is overset 0.000 years away. The void is not just large, it is time. It is years, decades, centuries, and millennia embodied in empty space. Every light year between us and another star is a year of travel at impossible speed, a decade at achievable speed, a millennium at current speed. The distances are not merely inconvenient, they are civilizationally significant. They are evolutionarily significant. They are geologically significant. And Proxima Centauri is just the beginning, the nearest star. The closest island in an ocean that contains hundreds of billions of islands, scattered across a galaxy 100,000 light-years wide. We have not even begun to discuss the true scale of our isolation. We have been measuring the puddle while ignoring the sea. Now, let us look up. Let us turn our gaze from the nearby stars to the galaxy itself. Let us see what 100,000 light-years really means, and understand why the Milky Way is not a civilization waiting to be united, but a graveyard of light too old to be relevant. Chapter 6. The Galactic Graveyard. The Milky Way stretches across the summer night sky like a river of spilled milk, a faint, luminous band arcing from horizon to horizon. Ancient peoples saw gods and monsters in its glow. Modern astronomers see something far more humbling, a spiral galaxy of roughly 200 billion stars arranged in sweeping arms around a supermassive black hole. The whole structure spans 100,000 light-years from edge to edge. Ibai. 000 light-years. Let those words sink in. Light, traveling at the maximum speed the universe permits, takes 100,000 years to cross our galaxy. That is not a journey. That is a span of time longer than modern humans have existed, longer than civilization. longer than the entire recorded history of every culture on Earth, multiplied by 10. Imagine you are immortal. Imagine you could strip away your biological body and become a being of pure energy, capable of traveling at the speed of light itself. You decide to cross the galaxy, to journey from one edge to the other, to see what lies on the far rim of this island of stars we call home. You begin at the outer edge in the sparse halo where ancient globular clusters drift like lonely lighthouses. You accelerate to light speed instantly, feeling nothing because you have no body to feel with. You become a photon, a quantum of electromagnetic radiation, the fastest thing in creation. You fly, and you fly, and you fly. After 10,000 years, you check your progress. Behind you, the outer edge has receded into a smear of distant light. Ahead of you, the galaxy still stretches endlessly. You are still in the suburbs, the thin outer disk where stars are sparse and the darkness between them yawns wide. On Earth, if anyone remembers Earth, sure, 000 years have passed. The pyramids have crumbled to sand. The languages you knew have evolved beyond recognition or vanished entirely. Nations have risen and fallen and been forgotten. You are still nowhere near the center. After 50,000 years, you pass through the galactic midplane. The density of stars increases. You are threading through spiral arms now, regions of active star formation where young blue giants blaze with the brilliance of a million suns. Nebulae glow in colors your human eyes could never have seen, excited by radiation from newborn stars. On Earth, whoosha, 000 years have elapsed. Homo sapiens may have evolved into something unrecognizable, or gone extinct, or spread to other worlds if they ever solved the problem of interstellar travel. You do not know. You cannot know. You are a beam of light, and information cannot catch up to you. After 100,000 years, you reach the far edge. The journey is complete. You have crossed the entire Milky Way galaxy at the maximum possible speed, and it has taken you 100 millennia. Now turn around. Look back at where you started. Look back toward Earth. If Earth still exists, if the sun still shines, if anything you knew remains, what do you see? You do not see the future. You do not see what became of humanity in the 100,000 years since you left. You see the past. You see light that left Earth 100,000 years ago, when you began your journey. You see a planet of ice and wilderness, gripped in the last glacial period. You see early humans, Homo sapiens, just beginning their great migration out of Africa, huddled in caves, striking flint to make fire, afraid of the dark. You see your ancestors. This is the time machine effect of light-speed travel. When you look across the galaxy, you do not see the universe as it is. You see a museum. Every photon that enters your eyes carries information from the past. The further the source, the older the information. Looking out is looking back. Consider Betelgeuse, the red supergiant star that marks the shoulder of Orion. It blazes in the winter sky, distinctly orange, one of the brightest stars visible to the naked eye. Betelgeuse is approximately 640 light-years away. The light reaching your eyes tonight left that star around the year 1385. During the reign of Richard II in England, before the printing press, before Columbus, before the Protestant Reformation, Betelgeuse is dying. It is a massive star in the final stages of its life, swelling and pulsing as it burns through its remaining fuel. Sometime in the next 100,000 years, it will explode as a supernova, briefly outshining the entire galaxy. When it happens, we will not know for 640 years. The light from the explosion will race toward us at 300 kilometers, carrying news of a death that might have already occurred. For centuries after Betelgeuse detonates, we will continue looking at its corpse, watching a star that no longer exists, navigating by its light, writing poetry about its beauty. We will be admiring a ghost. This applies to every star in the night sky. The closer ones, like Alpha Centauri, show us the past from just a few years ago. The more distant ones, like Deneb, show us the past from over 2,000 years ago. The stars of other galaxies show us millions or billions of years into the past. Some of the stars you see tonight may have burned out 1,000,000 years ago, but their light is still traveling, still carrying the image of something that no longer exists. The Milky Way is not a unified place. It is not a city where citizens can communicate and trade. It is a collection of 100 billion lonely islands, each separated from the others by oceans of time so vast that no meaningful connection is possible. If you sent a message to a civilization on the other side of the galaxy today, that message would take 100,000 years to arrive. If they sent a reply immediately, it would take another 100,000 years to return. A simple hello would span 200,000 years. By the time the conversation completed, both civilizations would likely be extinct or transformed beyond recognition. Physics tells us that nothing can influence anything else faster than light. This is called causality. It means that events separated by distances greater than light can traverse in a given time are causally disconnected. They cannot affect each other. They exist in isolation. If a civilization on the far side of the Milky Way destroys itself today, the gravitational waves from their dying star, the light from their final moments, the radio signals of their last transmissions, none of it will reach us for 100,000 years. For all that time, from our perspective, they are still alive. Their destruction has physically happened, but causally it has not. The universe has not yet informed us of their fate. We exist in a bubble of ignorance bounded by the speed of light. This creates a profound sense of isolation. There is no galactic now. There is no moment that is simultaneous across the Milky Way. The present is local. The further you look, the further into the past you see. The universe is not a snapshot. It is a layered archaeological dig, with the deepest layers representing the most distant reaches of space and time. Even if intelligent civilizations are common in the galaxy, even if there are millions of them spread across the spiral arms, communication between them would be essentially impossible on any meaningful timescale. A conversation spanning tens of thousands of years is not a conversation. It is archaeology. It is leaving graffiti on a wall and hoping someone reads it long after you are dead. The Milky Way may be teeming with life, or it may be empty except for us. We cannot know because the distances are too great and the speed of light is too slow. We are islanders who can see other islands on the horizon, but can never reach them, can never speak to their inhabitants, and can never know if anyone is home. And the Milky Way is just one galaxy among hundreds of billions, beyond its edges, separated by voids of millions of light years. Other galaxies spin in the darkness. The light from those galaxies takes so long to reach us that we see them not as they are, but as they were when the Earth was young, when life was simple, when the universe itself was a fraction of its current age. The prison of light speed is not a wall around our solar system. It is a cage around our entire island of stars, and that cage is shrinking, not because the speed of light is changing, but because the universe itself is expanding, carrying the other galaxies away from us faster than we can ever hope to reach them. Chapter 7. The Expanding Prison. For a long time, we thought space was static, a vast stage on which the cosmic drama played out. Stars were born and died, galaxies rotated, planets orbited, but the stage itself did not change. The universe simply was, eternal and unchanging in its basic geometry. In 1929, Edwin Hubble shattered this assumption. Working at the Mount Wilson Observatory in California, using what was then the largest telescope in the world, Hubble made a discovery that would rewrite our understanding of the cosmos. He found that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This was not ordinary motion. Galaxies were not flying through space like bullets. Space itself was stretching. The fabric of the universe was expanding, carrying the galaxies along with it like raisins in rising bread dough. The galaxies were not moving through space. The space between them was growing. Imagine the universe as a rubber sheet. Galaxies are dots painted on the sheet. If you stretch the sheet, the dots move apart from each other. But they are not actually traveling across the rubber. The rubber itself is expanding, and the dots ride along passively. This is how cosmic expansion works. Space is the rubber sheet. Galaxies are the dots, and the sheet is stretching in all directions, everywhere, all the time. This changes everything about the prison of light speed. We established earlier that light travels at 300 km/s. Sir, nothing can exceed this speed. But there is a crucial caveat. This limit applies to objects moving through space. It does not apply to space itself. Space has no speed limit. Space can expand at any rate the universe dictates, including rates faster than light. Consider a galaxy very far away, billions of light years distant. The space between us and that galaxy is expanding. New space is being created all the time, stretching the distance. If the galaxy is far enough away, the space between us is expanding so rapidly that it exceeds the speed of light. Wait, did we not say nothing can travel faster than light? Yes, but the galaxy is not traveling through space faster than light. It is sitting still in its local region of space, just as we are sitting still in ours. The space between us is what is growing, and space is not bound by the cosmic speed limit. This creates a horizon, a boundary beyond which the expansion of space outpaces the speed of light. Galaxies beyond this horizon are receding from us faster than light can travel. Any light they emit, racing toward us at the maximum permitted speed, is fighting a losing battle. The light moves forward at 300 km/s, but the space in front of it is expanding faster, like a swimmer trying to swim upstream against a raging river. The light makes no progress. In fact, relative to us, it falls further and further behind. That light will never reach us ever, no matter how long we wait. No matter how powerful our telescopes become, the galaxies beyond the cosmic horizon are permanently cut off from us. They exist, presumably, in some objective sense, but we can never see them, never contact them, never know anything about them. They are outside the observable universe. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang. Its radius is about 46 billion light-years in every direction. This might seem paradoxical. If the universe is only about 8 billion years old, how can we see objects 46 billion light-years away? The answer is expansion. The light we see today from the most distant objects began its journey when those objects were much closer to us. As the light traveled, space expanded behind it, stretching the distance. The objects that emitted that light are now much farther away than they were when the light set out. Think of it this way. A photon left a distant galaxy 13 billion years ago, when that galaxy was perhaps 1 billion light-years from us. The photon flew toward us at light speed, but as it traveled, space expanded. By the time the photon arrived, the galaxy that emitted it had been carried away by the expansion of space. It is now 46 billion light-years distant. We see the galaxy as it was 13 billion years ago, but its current location is far beyond where we see it. This is mind-bending. The universe we observe is not the universe as it currently exists. It is a historical record, a collection of snapshots from different epochs, layered like sediment in rock. The further we look, the older the light, the younger the universe we see. And here is the truly terrifying part. The expansion of space is accelerating. In 1998, two teams of astronomers made the same shocking discovery independently. By measuring the brightness of distant supernovae, they found that the expansion of the universe is not slowing down. As everyone had expected, it is speeding up. Something is pushing the galaxies apart faster and faster over time. We call this something dark energy. We do not know what it is. We cannot see it, touch it, or detect it directly. We only know it exists because of its effect on the expansion rate. Dark energy makes up roughly 68% of the total energy content of the universe, and its influence is growing. As dark energy drives the expansion to accelerate, more and more galaxies are pushed beyond the cosmic horizon. Right now, we can see billions of galaxies. We can photograph them, analyze their light, study their structure, but every second more of them slip over the edge. The horizon is shrinking, not because it is moving inward, but because the expansion beyond it is speeding up. In the far future, billions of years from now, the night sky will be empty of extragalactic light. The Milky Way will have merged with Andromeda and a few other nearby galaxies, forming a single giant elliptical galaxy. But beyond this local island, there will be nothing. All the other galaxies will have been carried away by the expansion of space. Their light will have redshifted into invisibility, their existence rendered permanently unknowable. Future astronomers in that era will look up and see only their own galaxy. They will have no evidence that other galaxies ever existed. They will have no way to measure the expansion of the universe because there will be nothing to measure it against. They will think the universe is a single island of stars floating in an infinite void, static and eternal, and they will be wrong. But they will never know it. We live in a privileged time. We can still see the evidence of the Big Bang. We can still observe the cosmic microwave background radiation, the afterglow of the hot, dense state from which the universe emerged. We can still measure the redshift of distant galaxies and infer the expansion rate. In the far future, none of this will be possible. The evidence will have been erased by the expansion itself. The speed of light, combined with the expansion of space, creates a trap that grows tighter over time. Not only can we not travel to distant galaxies, we cannot even see most of the universe that exists. The observable universe, 46 billion light-years in radius, is only a fraction of the whole. And even within that fraction, most galaxies are already beyond our reach. Scientists have calculated the reachable universe. If we built a spacecraft today, a spacecraft capable of traveling at 999% of the speed of light, and we launched it right now, how far could it go before the expansion of space made further progress impossible? The answer is sobering. Approximately 94% of the galaxies we can currently observe are already permanently beyond reach. Even at near light speed, even with perfect technology, even with infinite fuel, we could never visit them. The expansion has already won. The river is already too fast. We are restricted to roughly 6% of what we can see, and that number shrinks every moment. Every second that passes, another star slips over the horizon. Another world becomes unreachable. Another potential civilization is cut off from us forever. The universe is deleting files, erasing possibilities, closing doors, and we are powerless to stop it. The speed of light is not just slow, it is too slow to outrun the expansion of space itself. We are not merely imprisoned, we are imprisoned in a cell that is shrinking. The walls are closing in, the darkness is growing, and there is nothing we can do but watch. Chapter 8. Dreams of Escape. Humanity does not accept limitations gracefully. Throughout our history, we have encountered barriers that seemed insurmountable and found ways around them, through them, and over them. The sound barrier was broken in 1947. The gravity well of Earth was escaped in 1957. The surface of the Moon was walked upon in 1969. Every generation faces its impossible challenge, and every generation finds heroes willing to attempt the impossible. the speed of light is different. It is not an engineering problem waiting for better technology. It is not a material science challenge requiring stronger alloys. It is a fundamental law of physics, woven into the mathematics that describe reality itself. Einstein's equations do not merely suggest that light speed cannot be exceeded. They demonstrate that the concept of exceeding it is meaningless, like asking what is north of the North Pole. And yet we dream, we scheme, we search for loopholes. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a paper that electrified the science fiction community and intrigued serious physicists. He asked a deceptively simple question: what if, instead of trying to move a ship faster than light through space, we move the space around the ship? Einstein's general relativity tells us that mass and energy curve space-time. Massive objects like stars create dips in the fabric of space, and smaller objects roll into those dips, which we perceive as gravitational attraction. But if mass can curve space, perhaps other configurations of energy could do more dramatic things. Perhaps space could be stretched and compressed in controlled ways. Alcubierre imagined a bubble. Inside the bubble, space is flat and normal. A ship floats there, experiencing no acceleration, no time dilation. Nothing unusual, but around the bubble, something extraordinary happens. In front of the bubble, space contracts. It crunches together, compressing the distance between the bubble and its destination. Behind the bubble, space expands. It stretches out, increasing the distance between the bubble and where it started. The effect is like a wave in space-time. The bubble surfs this wave, carried forward by the contraction ahead and the expansion behind. The ship inside never moves faster than light through its local space, but the bubble itself, the wave of distorted space-time, can move at any speed, even faster than light. This is the Alcubierre drive, the warp drive, the theoretical basis for faster-than-light travel that does not violate Einstein's equations. There is, of course, a catch. There is always a catch. To create this bubble, to contract space ahead and expand it behind, you need something that does not exist in the everyday universe. You need negative energy, negative mass, exotic matter. Ordinary matter has positive mass. It attracts other matter gravitationally. It curves space in predictable ways. Negative mass would do the opposite. It would repel ordinary matter. It would create gravitational hills instead of valleys. It would push space apart instead of pulling it together. We have never observed negative mass in nature. We have no idea how to create it in a laboratory. Quantum field theory suggests that certain exotic configurations might produce regions of negative energy density, such as the Casimir effect between parallel conducting plates. But these effects are minuscule, far too small to power a warp drive. When Alcubierre first did his calculations, he found that creating a warp bubble large enough to hold a ship would require more negative energy than exists in the entire observable universe, an infinite amount of impossibility. Subsequent refinements by other physicists have reduced this requirement dramatically, but even the optimized versions require Jupiter masses of exotic matter that we cannot produce and do not know how to acquire. There are other problems. A warp bubble traveling through space would sweep up particles along its path into stellar dust. Hydrogen atoms, cosmic radiation. These particles would accumulate at the leading edge of the bubble, accelerated by the distorted spacetime. When the bubble stopped, when the warp drive shut down, all that accumulated energy would be released in a single devastating pulse, a beam of high-energy particles and radiation directed at whatever lay ahead. You would not arrive at your destination. You would arrive with a death ray. The planet you came to visit would be sterilized by your arrival. The warp drive might be a weapon of mass destruction masquerading as a transportation system. What about wormholes? The classic shortcut of science fiction. A tunnel through space-time connecting two distant points. Einstein and his collaborator Nathan Rosen discovered in 1935 that the mathematics of black holes seem to allow for bridges. A black hole, that ultimate gravitational pit from which nothing escapes, might connect to another black hole somewhere else in space or time, fall into one end, emerge from the other, skipping the intervening distance entirely. If wormholes exist, and if we could stabilize them, and if we could survive passage through them, the prison walls would crumble. We could step from Earth to Proxima Centauri in a moment. We could cross the galaxy in an afternoon. Distance would become meaningless. But natural wormholes, if they exist at all, are thought to be microscopic, quantum fluctuations in space-time, appearing and disappearing in fractions of a second. To use one, we would need to grab it, expand it to human scale, and hold it open. Holding it open is the problem. Gravity wants to crush a wormhole shut. The moment anything tries to pass through, the throat collapses. To keep the door open, you need a doorstop. You need, once again, exotic matter with negative energy density. You need to line the walls of the wormhole with anti-gravity to push against the crushing force. Even if we could create and stabilize a wormhole, there is a deeper problem. A wormhole that allows faster than light travel also allows time travel, and time travel creates paradoxes. If you can travel faster than light in one reference frame, special relativity guarantees that you can travel backward in time in another reference frame. This is not an engineering limitation. This is geometry. The mathematics are unavoidable. Faster than light travel and time travel are the same thing viewed from different angles. Stephen Hawking proposed what he called the chronology protection conjecture. He believed that the laws of physics conspire to prevent time travel. Whenever you try to create a time machine, something goes wrong. Quantum effects destabilize the system. Energy builds up to infinity. The universe protects its timeline by destroying anything that threatens to alter it. If Hawking is right, warp drives and wormholes may be impossible not because of engineering difficulties, but because the universe does not permit closed time-like curves. The speed of light is the speed of causality, and causality must be preserved. Perhaps the prison exists for a reason. Perhaps the walls are there not to punish us, but to protect the universe from paradoxes, from effects preceding causes, from the logical chaos of a timeline that can be rewritten. Or perhaps we simply have not found the loophole yet. Perhaps some future Einstein will discover a way around the equations, a configuration of space-time that allows transit without time travel, a bridge that does not require exotic matter. Physics has surprised us before. It may surprise us again. But we cannot count on miracles. We cannot plan our civilization's future around theoretical possibilities that may never materialize. The warp drive remains a dream, beautiful and tantalizing, probably forever out of reach. So if we cannot cheat the distance, perhaps we must simply endure it. Perhaps the answer is not speed, but time. Perhaps we must become a species that thinks in centuries and millennia, that sends ships which take generations to arrive, that accepts the prison of light, speed, and learns to live within its walls. Chapter 9. The Paradox of Time. If we cannot break the speed limit, perhaps we can outlast it. This is the logic of the generation ship, that staple of science fiction, that audacious answer to the tyranny of distance. If a journey takes 10,000 years, send a ship designed to sustain a population for 10,000 years. Let the travelers breed and die and breed again. Let generations rise and fall in metal corridors between the stars. The grandchildren of the grandchildren of the grandchildren of those who launched will be the ones to arrive. The concept is brutally simple. Build a vessel large enough to be a world, a spinning cylinder to create artificial gravity, forests and lakes and farms to provide food and oxygen, and psychological relief from the claustrophobia of eternal transit. Launch it toward a distant star at whatever speed your technology permits. Wait, the first generation would be heroes, pioneers who chose this fate, who accepted that they would never see their destination, who gave their lives so that their descendants might walk on another world. They would remember Earth. They would carry its culture, its languages, its accumulated wisdom. They would teach their children about blue skies and open oceans and the feel of wind on skin. The second generation would be born in transit. They would know Earth only through stories and recordings. An abstraction, a myth of a place their parents came from. They would grow up in corridors, breathing recycled air, eating food grown under artificial light. The ship would be their entire universe. The stars visible through portholes would be decorations, not destinations. By the 10th generation, Earth would be legend. By the 100th, it might be forgotten entirely. Language would drift, without contact with the home world, without fresh cultural input. The speech patterns of the ship would evolve in isolation. After a few centuries, the language spoken aboard might be incomprehensible to speakers of the original tongue. The technical manuals written in ancient English or Mandarin, or whatever language the founders used, would become sacred texts, recited by rote without understanding. And what would sustain them? What would give meaning to generation after generation, born and dying in a metal tube, never arriving, never accomplishing the mission they inherited? The destination would become a religion. The promised land, the paradise awaiting at the end of the journey. Stories would be told of the world to come, of open skies and solid ground, and water falling from clouds. Children would dream of it. Adults would work toward it. The elderly would die hoping their descendants would achieve it. But hope is fragile across such timescales. What happens in year 5000 when the destination is still 5,000 years away? When no one alive has ever known anything but the ship? When the arrival is as distant in the future as the departure was in the past? A journey of 10,000 years means 500 generations of people who will never see either end, who are born in the middle and die in the middle, and pass the torch to children who will also die in the middle. Sociologists who have studied long-duration space missions warn of the psychological toll depression, ennui, loss of purpose. After enough generations, the inhabitants might forget they are on a ship at all. They might come to believe that the metal walls are the boundaries of existence, that the hum of the engines is the voice of God, that the destination is a fairy tale invented by ancestors who no longer matter, or they might rebel. Some generation might decide they do not want to spend their lives serving a goal they will never achieve. They might vote to turn the ship around, to go home, except home no longer exists as they knew it. Or they might simply stop maintaining the systems. Let entropy take its course. Allow the ship to become a tomb drifting forever through the dark. The generation ship solves the problem of distance by creating a new problem. The problem of meaning. The problem of sustaining purpose across timescales no human society has ever attempted. Civilizations on Earth have risen and fallen in less time than such a journey would take. Empires have crumbled. Languages have died. Entire peoples have vanished from history. What hubris makes us think a ship could succeed where continents have failed? There is another option. Suspend the passengers. Freeze them. Put them to sleep for the duration of the journey, and wake them only at arrival. Cryonics offers a seductive vision. Close your eyes on Earth. Open them at Proxima Centauri. Skip the boring part. Arrive refreshed and ready to explore, biologically unchanged from the day you departed. Some animals do this naturally. The wood frog freezes solid every winter, its heart stopping, its blood crystallizing, its metabolism dropping to zero. In spring, it thaws and hops away as if nothing happened. Certain species of fish and insects survive similar suspended states. If biology can manage it, perhaps technology can too. But a human being is not a frog. Our brains are vastly more complex, more sensitive to the damage caused by ice crystal formation. Freezing a human being with current technology means killing them in a way that cannot be reversed. The ice ruptures cell membranes, destroys the delicate structures of neurons, even if we could thaw the body. The person who went in would not be the person who came out. They would be dead tissue that used to be a person. Research continues. Scientists explore vitrification, converting tissues to a glass-like state without ice crystal formation. They study suspended animation in other species, looking for chemical tricks that might apply to humans. Progress is made slowly, incrementally, but the gap between freezing a frog for 1 winter and freezing a human for 70,000 years is not a gap that incremental progress will easily close. And even if we solve the biology, we face the engineering. A ship carrying frozen passengers still needs to function for millennia. Computers must run without crashing. Power systems must generate electricity without interruption. Navigation must remain accurate despite the movement of stars over cosmic timescales. Life support must protect fragile frozen bodies from radiation, from micrometeorites, from the 1,000 things that can go wrong in the void. Who tends the sleepers? Artificial intelligences. Presumably machines smart enough to handle any contingency, patient enough to wait for thousands of years, reliable enough to never fail. We do not have such machines. We do not know how to build them, and even if we did, we would be trusting our lives to systems that must operate perfectly for longer than any human technology has ever functioned. What if the AI degrades? What if cosmic rays flip bits in its memory, slowly corrupting its programming? What if it decides after 10,000 years of solitude that its mission no longer matters? What if it develops the machine equivalent of madness, alone in the dark for longer than human civilization has existed? The sleepers would never know. They would drift through the void, frozen and helpless, their fate in the hands of a system that might fail at any moment for any reason, with no one to notice or repair the damage. They might arrive at their destination as planned, or they might drift forever, a silent tomb of frozen dreamers who never woke. There is a deeper question lurking beneath these practical concerns, a philosophical puzzle that haunts all schemes for interstellar travel. If a journey takes 70,000 years, who arrives? Not the people who left. They are dead, no matter how well preserved. Not the civilization that launched them. It too is dead, transformed beyond recognition by the passage of time. The beings who step off the ship at journey's end will be strangers to everyone who planned the mission. They will carry the genes of the founders, perhaps, but not their culture, not their memories, not their dreams. When we imagine sending humans to the stars, we imagine continuity, us spreading outward, our children inheriting the galaxy. But at these timescales, there is no continuity. There is only replacement, generation after generation, each one dying, so the next can carry the torch a little further, until finally someone arrives who has no connection to anyone who departed. Who is a new species evolved in metal corridors, shaped by selection pressures we cannot imagine? Is that victory? Is that what we mean when we talk about humanity reaching the stars? Or is it something else entirely? A different story written by different beings in a language we would not recognize. The speed of light forces us to confront what we mean by we. It stretches the definition of humanity across timescales that dissolve identity. It asks whether a species that takes 100,000 years to cross the galaxy is still the same species at the beginning and end. It suggests that the prison might not be the walls themselves, but the brevity of our lives within them. Chapter 10. The meaning of the cage. We have journeyed far, from the snap of fingers to the edge of the observable universe. From Ole Roma timing the eclipses of Io to Einstein rewriting the laws of physics, from the 8-minute delay to our sun, to the billions of years of light travel that separate us from the most distant galaxies we can see. We have stared into the void and measured its vastness. We have confronted the prison of light speed and found its walls unyielding. The conclusions are stark. We cannot exceed the speed of light. We cannot even reach it with any object that has mass. The distances between stars are so great that travel times, even at impossible speeds, stretch into years. decades, and centuries. The distances between galaxies are so vast that they stretch into millions and billions of years, and the expansion of space is carrying most of the universe beyond our reach forever, shrinking the cage even as we struggle against its bars. It would be easy to despair, to look at these numbers and conclude that we are doomed to die on this rock, or perhaps this solar system, never knowing what lies beyond, never touching the stars we can see, never answering the questions that burn in our curious minds. Easy to see the speed of light as a cosmic cruelty, a taunt, a window showing us wonders we can never possess. But perhaps we are looking at it wrong. Perhaps the prison is also a sanctuary. Consider what the universe would be like without the speed limit, without the finite propagation of light, gravity, and causation itself. If everything could travel instantaneously, there would be no isolation. Every point in the universe would be in immediate contact with every other point. The gravity of 1 trillion galaxies would tug on our solar system simultaneously. Orbits would be chaotic, unpredictable, unstable. The gentle dance of planets around stars, stars around galactic centers, galaxies around each other, all of it depends on the finite speed at which gravitational influence propagates. Without that limit, the universe would be a churning chaos of instantaneous interactions, nothing in equilibrium, nothing stable long enough for complexity to emerge. If light traveled infinitely fast, the night sky would not be dark. It would be blindingly bright, flooded with the instantaneous radiation of every star that has ever shone. The sky would be a wall of fire, the gentle scatter of stars across the darkness, the beauty of constellations, the wonder of distant galaxies glimpsed through telescopes. All of it exists because light takes time to travel, because distance translates to delay, because we see the universe in layers of history rather than all at once. The speed of light creates islands. It separates regions of space into causally distinct zones that can evolve independently. A planet can form around a star without being disrupted by events in a distant galaxy. Life can emerge in a quiet corner of the cosmos without being sterilized by radiation from the other side of the universe. Civilizations can rise and fall without every other civilization knowing immediately. We exist because the universe is slow. We are possible because light takes time. The prison walls are also the walls of a nursery, protecting us from a cosmos that would otherwise be too connected, too chaotic, too bright, too violent for complexity to survive. And consider what the distance means for our appreciation of what we have. There is no planet B. Not really. Not reachably. Proxima Centauri B might be a rocky world in the habitable zone of its star. It might have liquid water. It might even have life. But it is 4 years away at light speed. Tisha, 000 years away at our fastest current technology. For all practical purposes, for all purposes that matter to us as biological creatures with finite lifespans, there is only Earth. This rock, this pale blue dot, this seemingly insignificant speck in the cosmic ocean is everything we have. Every human who has ever lived was born here. Every ecosystem, every species, every forest and ocean and mountain range, everything we love, everything we have built, everything we might become. It is all here, and it is all we can reach. The distance to the stars forces us to cherish what we have. It forces us to take care of this planet because there is nowhere else to go if we ruin it. It focuses our attention on the here and now, on the problems we can solve, on the world we can improve. The dream of escape to other worlds is beautiful, but its impossibility on human timescales means we must deal with our problems where we are. And yet the dream itself has value. The stars call to something deep in our nature, the desire to explore, to discover, to know what lies beyond the horizon. This drive has pushed humanity out of Africa, across oceans, to the poles and the peaks, and eventually to the moon. It will not be satisfied by being told the next horizon is forever out of reach. Perhaps the answer is not to travel ourselves, but to send our children, not biological children who would take generations to arrive, but mechanical children, robots, probes, self-replicating machines that can cross the void at whatever speed physics permits and send back what they learn. A spacecraft does not need life support. It does not need food or water or air. It does not grow bored or depressed or rebellious. It can be radiation hardened to survive the centuries. It can be small and light, easier to accelerate than a crude vessel. And if it carries the ability to replicate itself using materials found at its destination, a single probe could become 1,000,000 probes, spreading through the galaxy at a pace no biological species could match. We call this concept the von Neumann probe. After the mathematician who first described self-replicating machines, launch one, it travels to the nearest star. It lands on an asteroid, mines the rock, builds copies of itself. Those copies launch to other stars. They arrive, replicate, launch again. Exponential growth. A wave of exploration spreading outward at some fraction of light speed, eventually reaching every star in the galaxy, even at 1% of light speed. Such a wave could cross the entire Milky Way in 10 million years. A long time by human standards, but a blink of an eye in cosmic terms. The galaxy is over 13 billion years old. 10 million years is less than 1,000th of its history. If any civilization had launched von Neumann probes billions of years ago, they would have filled the galaxy by now. Perhaps we will be that civilization. Perhaps our legacy will not be footprints on distant worlds, but probes carrying our knowledge, our art, our questions into the void. Perhaps we will touch the stars, not with our hands, but with our machines. And through them, we will learn what is out there, even if we can never go ourselves. Or perhaps we will send something stranger patterns. Information. The uploaded minds of those who choose to become data, transmitted at light speed across the galaxy, arriving as signals to be received and reconstructed at the other end. We might not travel as bodies, but we might travel as souls, if the technology ever permits such a transformation. These possibilities do not solve the problem of light speed. They do not break the prison walls, but they suggest that the walls are not as absolute as they seem, that there are ways to reach beyond them, even if we ourselves cannot pass through. Tonight, if the sky is clear, go outside, look up at the stars. Do not look at them with frustration as places you will never visit. Do not look at them with despair as reminders of your cosmic insignificance. Look at them with wonder, with gratitude, with the knowledge that for a brief, shining instant in the middle of the cold dark, you are awake and aware and able to see them at all. The light touching your eyes has traveled for years or centuries or millennia. It carries news from the past, glimpses of worlds as they were long ago. You are seeing the history of the universe spread across the sky like a living museum. No other creature on this planet can comprehend what those points of light really are. Only you, only humans, only this strange species that evolved curiosity along with consciousness. We are the prisoners of speed. We are trapped in a cage of light years and expansion and the fundamental laws of physics. But we are also the keepers of knowledge, the askers of questions, the dreamers of impossible dreams. We built telescopes to see farther than our eyes could manage. We built mathematics to understand what we saw. We built rockets to escape our atmosphere and probes to explore our solar system and theories to explain the cosmos. The cage is real. The bars are solid. We may never break them, but we have learned to see through them. We have learned to send our machines through them. We have learned to throw our minds across them in waves of electromagnetic radiation, carrying our thoughts and our art and our hopes. The speed of light is slow, agonizingly, tragically, terrifyingly slow when measured against the scale of the universe. But it is also the speed at which we send our voices into the void, hoping someone is listening. It is the speed at which we receive news from distant stars, learning about worlds we will never walk upon. It is the connection, however thin, between our island and all the other islands scattered across the cosmic ocean. We are alone and we are connected. Both things are true. The universe is vast beyond comprehension, and the speed of light makes it vast still. But we are here. We are conscious. We are reaching. And as long as we keep reaching, the dream is not dead. The stars await, even if we can only touch them with light. If you found this journey through the cosmos enlightening, if you understand now why the speed of light is both our greatest achievement and our most profound limitation, please like this video and subscribe to the channel. Your support makes these explorations possible. Tell me in the comments what aspect of cosmic distance disturbs you most. Is it the loneliness, the time scales, the expanding horizon that swallows galaxies, or something else entirely? And tell me what you would send to the stars if you could. A message, a probe, a piece of music, a memory. What would you want to represent humanity in the void, knowing it might travel for millennia before anyone receives it? The universe does not care about our questions, but we do. And that caring, that wondering, that refusal to accept ignorance, that is what makes us human. That is what makes us the keepers of the light. Thank you for watching.